Hi there, it's Paul Bamberg with the first of one of the proofs scripts. This is an R script designed to illustrate the results that are proved in week 1 of Math156. You should probably have the statements of the proofs out in front of you as you watch this video, and it's a matter of taste whether you watch this before or after the video in which I do the proofs. You can either say, I'll watch this first, then I'll be curious about why these numbers turn out to be equal, and I'll want to see the proof that shows they're always the same. Or you might go through the proofs first and say, I'd just like to back this up with some examples in specific cases. Up to you. So let's get started. In script 0D, which I did in the first class, I created a file containing the 216 possible outcomes when you roll 3 fair dice, and I stored it in a file named dice3.csv. When I wrote that file, the Excel file contains in its first column the numbers 1 through 216. Those are the row names. I don't really want to load those separately, and that's why I say row.names equals 1. It says those are the names of the rows, they're not actual data. So we load it, and then just as a sanity check, I ask how many rows are there. You can see down in the lower pane there are 216, and the function head always gives me the first 6 rows, and I can see, yes indeed, I am getting all possible results for 3 dice. Now we can create some random variables based on these. Probably the most obvious one is the sum of the rolls on the 3 dice. So I take dice3 $red3, that says the first column, plus the second column, plus the third column, and I assign that to sum3. And the great thing about R is this is a vector operation, but it's done automatically. In other words, this sum3 is going to turn out to be a vector of 216 numbers. Head will give me the first 6 of them, and you can see, yes indeed, 3, 4, 5, 6, 7, and 8 are respectively the sums of rows 1 through 6. If I divide by 3, I get the mean roll on the dice. Yes, those numbers are smaller by a factor of 3. And notice again, division by 3 is an operation that R applies to the entire vector. Now I'm going to create some more subtle random variables. The larger of the numbers on the first 2 dice is a perfectly good random variable. There's a function in R named max that computes the largest of a set of numbers, but it's a little bit tricky to apply it just to the first 2 of the 3 numbers in the row. See what I've got after dice 3. I've got in square brackets nothing for the first index position. That's reasonable. That would be the row. And 1:2 in the second position. That says use just the first and second entries in each row. The one that follows means apply the given function row by row, and the function that I'm going to apply is max. I'm going to store the result in max2, and sure enough, for all of the first 6 rows, the larger of the 2 numbers was a 1, and that's what I've got. I should say it took me a while to figure out how to make this apply function work, and I have to look it up when I want to use it in a slightly subtle way like this. Another random variable is the difference between the largest number showing and the smallest number showing. I can apply max and min to the row, take the difference, and that gives me the range I want. And as is my style, I always print out the head of the vector that I've calculated just to make sure I haven't done anything wrong. So now we've got several more random variables, and let's append to our existing data frame that we got by loading the Excel file these three columns. There's a function called cbind, short for column bind, that does precisely that. So I bind to dice 3, sum 3, max 2, and range. And when I look, I see, yes indeed, I have now got a data frame that has 6 columns in it with 6 random variables. Now, what we're doing here is probability, not statistics. We've got 216 rows, but they're not 216 rows randomly chosen from some larger population. They are the entire population, with each row being equally likely. And R doesn't have a function that computes variance in that case, so we have to write our own. We're defining a function that acts on a vector x. And what does it do to compute the variance? Well, you remember the definition of variance. You take the mean of x, and having found that mean, you take, for each element of the vector, x minus the mean, you square that, and the mean of that result is the variance. That's the definition. When we apply this to sum 3, that's a column of the data frame, but it's also a vector that gives the sum of the 3 dice. The number that we calculate is 8.75. Now have a look at proof 1. Proof 1 shows that it's possible to do this calculation in a single pass through the data, because I can convert the definition of variance to the mean of the square minus the square of the mean. And sure enough, when I take that, I get 8.75. The proof shows that this always works. What about the variance of the mean? If instead of using the sum, I use the mean, I divide by 3, and one of the other proofs shows that if you divide a variable by 3, you divide its variance by 9. I'll calculate the variance of the mean, and then I will also print out 9 times var mean 3. That comes out to 8.75, which shows that my analysis was correct. Now let's go on to proof 2. Proof 2 says if you take a set of random variables that all have the same variance, the sum of n of them has a variance that's a factor of n larger if the variables are independent. The mean has a variance that's a factor of n smaller. So let's do this just for a single die roll. 1:6 creates a vector whose 6 elements are 1, 2, 3, 4, 5, 6, and I will store that under the name 1 die, and then I will calculate the population variance and store it as var 1. The value of that turns out to be 2.91. If I roll 3 dice and the rolls are independent, the variance for the sum of 3 dice should be 3 times that. So I multiply by 3. I compare that with var sum 3, and I get the same number. And this is not a trivial business. Notice to get var sum 3, I had to generate all 216 rows and take the variance. I get the same number much more easily by considering the variance of a single die roll and multiplying by 3. To get the mean, I divide by 3, and I replicate the number that I got earlier for the variance of the mean. Let's move on to proof 3, which is probably the most subtle of these. There is a built-in function in R called var. What that does is to assume that the data it's been given are a sample from a larger population, and what it tries to do is estimate as well as it can the variance of the underlying population. And what proof 3 shows is that if you want to do that, you divide by n minus 1 instead of dividing by n. So if you want to get the true population variance using this function, you have to multiply by n over n minus 1, after you've got the result. So there's var of 1 die. That is larger by a factor of 6/5 than the variance that we calculated earlier. Proof: the two numbers are the same. If I want to predict the value that the built-in function will give on the sum of 3 dice, what I do is take the population variance that I calculated and again multiply by n over n minus 1. Finally, let's have a look at the concept of independence. If two variables are independent, then the expectation of their product is the product of their expectations. So if we ever find a situation where the expectation of the product differs from the product of the expectation, we know that these variables are not independent. This is true, for example, of the range, largest minus smallest, and max 2, the larger of the rolls on the first 2 dice. The numbers we compute are different. That guarantees the variables are not independent. The same thing is true with the sum of all 3 dice and the larger of the rolls on the first 2 dice. It's fairly obvious that these two are not independent. For example, if the value of max 2 is 1, it means you got a 1 on the first 2 dice and the sum is going to be on the small side. The white die was the third die, and it does seem reasonable that the roll on the third die should be independent of the larger of the numbers on the red and green dice, and we pass the test that the expectation of the product equals the product of the expectations. That doesn't prove, however, that these two random variables are independent. What it proves, technically speaking, is that they're uncorrelated, and in fact there's a built-in function to check that in R. COR applied to these two columns in my data frame gives 0. That proves that the variables are uncorrelated. Remember that I proved that the expectation of the sum equals the sum of the expectations, independent of whether or not the random variables were independent. So using range and max 2, which we now know to be dependent, we can check that. The expectation of the sum, as given by mean, is equal to the sum of the expectations. For variance, however, I needed to assume independence in order to prove the same sum rule. And sure enough, if I calculate the population variance of the sum, range plus max 2, I get something that's quite different from the sum of the population variances individually. If, however, I use the two variables that I now know to be independent, namely the roll on the white die and the larger of the rolls on the first 2 dice, I get the same number. That proves, now it doesn't prove anything. What it shows is that my proof that the variance of the sum equals the sum of the variances for independent variables is borne out in practice. In fact, once you prove something, doing an example accomplishes nothing additional, but most of us like to see examples even when we're sure that something is true. When we add up independent random variables, we add their variances, and sure enough, if I take the sum of the 3 dice, its variance is 3 times the variance for the roll on just the red die. When I multiply a random variable by some constant a, I multiply its variance by a squared, and adding on a constant, this was one of the other proofs, doesn't make anything different. Sure enough, when I multiply by 3 and add 5, I increase the variance by a factor of 9. Recall that if variables are independent, any functions of those variables are also independent. So let's start with 2 independent variables, the roll on the third or white die and the max of the rolls on the first 2 dice. Now I can take any function of each variable. Taking the sign of a die roll is an absolutely insane operation. So is taking the exponential. But the theorem said any function, so I'll use any function. And sure enough, if I apply these two functions to the two random variables, the mean of the product of the functions equals the product of the means. If you have a couple of variables that are uncorrelated but not independent, they will fail this test, but you've got to find the right function in order for that to happen. A function that will provide a sufficient test is a function that gives 1 if a numeric random variable is less than or equal to some number x, 0 if it's greater than x. So let me store 2.4 in x and use those two functions. I get exactly the same results in both cases, but that doesn't prove anything. It could have been an accident. I would really have to show this for all values of little x. And there's no way of doing that computationally. This is the sort of thing that has to be done mathematically because no number of examples will make the point. So, to summarize, by computation you can verify that two random variables are uncorrelated. You can verify that they're dependent, that they fail to be independent, but there's no computational way of verifying that random variables are independent. That has to be done by mathematical proof. You might want to go back and look at the details of the proofs now, but we're done with this R script.